Hello everyone, this is Professor Roman. Welcome to the 49th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to talk about undirected networks and the minimum spanning tree problem. We've talked briefly about undirected networks. That was quite some time ago. And in this section, we're going to study them more seriously. An undirected network is a graph N for which each edge has been assigned a real number. That's what makes it a network. And that number is called the weight of the edge. The sum of the weights of all the edges in the entire network is called the weight of the network. We will study directed networks in a future video, but for this video, I'm going to use the term network to mean undirected network. And it is pretty clear that any subgraph of a network is also a network, because the edges still have the weights assigned to it from the original network. Here's a graph. This is an undirected network. The cities represent the vertices represent cities, and the weight of each edge is the distance by air between the corresponding cities. Obviously, this is the kind of network that has serious applications. Here's another network. In this case, the vertices V1, V2, and V3 represent factories that produce a certain product. And the vertices U1 and U2 represent retail outlets for that product. The weight of an edge is the cost of shipping a certain quantity, predetermined quantity, of the product from the factory to the store. These, instead of stores, they could be warehouses as well. Here's a network. The weight of each edge is the maximum number of cars that can travel along the road here. So this is a road map. So I think you can see, at least from these three examples, that this concept of a directed network has important applications to things like urban planning and manufacturing, and businesses and so on. Actually, any graph can be represented as an undirected network. So take a look at this graph, kind of a mess, but we can represent that in this way. The vertex set is the same, but what we have done is this is a complete graph with loops, and the weight of each edge in the network is equal to the number of edges between the corresponding vertices in the original graph. So for example, between V4 and V3, there are 3 edges. So that's why this edge here is labeled 3. And you might want to take a moment to convince yourself you can go back and forth. I mean, the network is defined by the graph, and the network will determine the graph as well. One of the most important problems associated with undirected networks is what is called the minimum spanning tree problem. And a popular version of this problem goes like the following. Here is a collection of cities, and suppose that a railroad company wants to build a railway system between the cities. this would apply in other circumstances too. Could be airlines, could be trucking companies, could be UPS, whatnot. The first step is for the company to determine how much it would cost to build, well, in the case of railroads, tracks between each pair of cities. And suppose that the costs in millions of dollars are given as the weights of the edges in this undirected network. So, for example, it costs $18 million to build railroad tracks from LA to Dallas. Well, naturally, the company wants to do this construction as cheaply as possible, so it's certainly not going to build all of the tracks in this network. But it does want to be able to take passengers from any one of the cities to any other, possibly through intermediate stops. In fact, almost likely through intermediate stops. The minimum spanning tree problem in this case is to determine which tracks the company should build in order to keep the total cost to a minimum. So from a graph theoretical point of view, the problem is to find a subgraph of N, the network, of smallest weight that is connected and has the same vertices as the network N. Well, that's got to be a spanning tree for the network. The subgraph shouldn't have any cycles because you can always, if it did, you pull out one of the edges and you still have a connected graph, and it would have smaller weight and still provide access between the cities. But not all spanning trees will solve the minimum spanning tree problem. Some spanning trees will have more weight than others. So here is one possible spanning tree that would allow you to get from any city to any other city. The total cost is $71 million, but this spanning tree has a total cost of only $36 million. It's a lot cheaper. So here's the definition then. If N is a connected, undirected network, the minimum spanning tree problem for N is the problem of finding a spanning tree of N of smallest weight, called the minimum spanning tree. And I'm leaving it to you to convince yourself that every connected, undirected network has at least one minimum spanning tree. I think you can do that in 2 sentences probably. There are several algorithms for actually finding a minimum spanning tree, and I'm going to discuss one now, one of the most famous. It's called Kruskal's algorithm. So let N be a connected, undirected network. Then the following greedy algorithm, and I'll explain that term in more detail a bit later if I haven't done so already, defines a minimum spanning tree of N. Choose a sequence of edges of N subject to the condition that at each step, for each choice, the edge chosen is one of smallest weight from among the remaining edges that do not form a cycle with the previously chosen edges. So choose an edge of minimum weight that does not form a cycle with what you've already chosen. And when that's no longer possible, the edges you've chosen along with the vertices will be a minimum spanning tree for the network. So the procedure is pretty straightforward. It's really just common sense, right? You just keep choosing edges of minimum weight without forming a cycle. The proof is a little bit trickier than the statement of the theorem, so let's go over it. Let K denote a subgraph of N, obtained by using Kruskal's algorithm. That's why I called it K. I'm going to leave it for you to show that K is at least a spanning tree. We've pretty much talked about this before. We need to show that K is a minimum spanning tree. Now, because N has only a finite number of spanning trees, it's a finite graph, it's got to have a minimum weight spanning tree, and I just gave away the proof of the previous theorem. I guess it was one sentence. So we can assume that M is a minimum weight spanning tree and that it's different from K, the one we got from Kruskal's algorithm. Otherwise, we're done. We've figured out that the Kruskal's algorithm did produce a minimum spanning tree. So we'll assume they're different for the moment. Now, we list the edges of both K and M in order of increasing weight. And we order the edges of M so that as many edges as possible in the two lists are the same. Okay. So here are the edges of K, E1 through En minus 1. Here are the edges of M, F1 through Fn minus 1. And E1 is equal to F1 and so on down to EK minus 1 equal to FK minus 1. This is where they first differ, and we don't know what's going on for the rest of them. Okay. If K equals 1, then there are no matching edges, which is certainly possible. Now, since EK is an edge of smallest weight that does not form a cycle with the previously chosen edges, that's Kruskal's algorithm, the weight of EK here is less than or equal to the weights of any of the F's starting at FK through Fn minus 1. And that's because, for example, if the weight of Fk was less than the weight of Ek, we made a mistake in Kruskal's algorithm. Instead of choosing Ek, we should have chosen Fk, because Fk doesn't form a cycle with F1 through Fk minus 1. Therefore, it's the same thing as saying it doesn't form a cycle with E1 through Ek minus 1. It has smaller weight than Ek, so we screwed up. Okay. So the weight of Ek is less than or equal to the weight of Fk, but the rest of these are in increasing order of weight, so that takes care of the rest of this. Now let's recall something I discussed with you some time ago, the edge replacement property of trees that I said would be useful. I think I said that property tells us that if we have a tree, we can insert an edge into the tree. It will create a unique cycle containing that edge. We can take out one of the other edges of the cycle and get a tree again. In this case, a spanning tree. And that's what I call the edge replacement property. So in this case, we can insert EK, this vertex here, into M, I'm sorry, did I say vertex? This edge into M. Okay. And then we have to pull something out, and we will now have, since EK doesn't form a cycle with E1 through EK minus 1, it doesn't form a cycle with F1 through FK minus 1. But when we put the additional edge EK into M, it does create a cycle containing EK. The point, however, is that that cycle has to contain one of these edges, FK plus 1, through, actually FK through Fn minus 1. Okay. So what happens then if we pull out that edge? Let's call that edge Fk plus j. It's K, j is, starts at 1 here. So we take M and we add the edge EK, and we pull out the edge Fk plus j. Well, the weight of EK is less than or equal to the weight of Fk plus j. So this new spanning tree, M prime, actually has weight less than or equal to the weight of the original M before we touched anything. But this was a minimum spanning tree, M. So these weights are actually equal. What we have done is we've produced a spanning tree M prime of minimum weight that contains another edge from K, namely EK. So we're inserting EK and removing one of the later edges, FK plus J. And then on this side, we still have a minimum spanning tree with one additional edge EK from the E side, from the Kruskal algorithm side. Well, we can keep doing that. And eventually, we will end up with a minimum spanning tree that has all the edges from K, and therefore it is K. And so that means that K is a minimum spanning tree. Okay, hope that was clear enough. It's probably worth going over again if it wasn't clear enough. And if you go over it a few times and it's still not clear enough, that's probably my fault for not explaining it well enough. But let's test out Kruskal's algorithm on this network. Okay, the algorithm is very simple. Just pick an edge of smallest weight. So I picked E3 here, has weight 0. Looking among the other edges, pick one of smallest weight that doesn't form a cycle with the edges we've already picked. That's no problem. I picked this one here. Do it again. Select this one, for example, weight 2. What's next? Here, weight 4. Pick this one. This is also weight 4, but it would form a cycle, so we can't pick it. And finally, this edge at the bottom, weight is only 5. This is weight 5, can't pick it. I've already picked this one. So, I guess I had 2 more steps to go. So I picked both of these 2 edges of weight 5, one at a time. Now we can't pick any more edges without forming a cycle. So we're done. And this is, in fact, a minimum weight spanning tree. You can add up the weights if you want, and we're done. Now, I said I would say something about greedy algorithms, so this is a good time. It's a little bit of an aside, but an algorithm is said to be greedy if each step selects the best possible choice at that moment without consideration of future consequences of that choice. And Kruskal's algorithm is an example of a greedy algorithm because at each step we simply find a single edge of smallest weight that doesn't form a cycle. It is conceivable, or it might have been conceivable, that that was a bad choice, that if we selected an edge of, say, a little bit larger weight, it might save us some weight in future selections. Not so. Greedy algorithms, I'm not an expert on algorithms, but generally are not the best approach. But Kruskal's algorithm is the best. Just to illustrate the problem with greedy algorithms, here's a little graph, and each vertex is given a weight in this case. And the problem is to find a set of totally disconnected, in other words, isolated vertices of maximum weight. So they're unconnected, no edges, just vertices of maximum weight. Now, what would the greedy algorithm tell you to do? At the first step, you pick the vertex of maximum weight, which is 2 here in the center. Well, then you're stuck. You can't pick any of the other 4 vertices because they're all connected to the vertex you've already chosen. So that gives you a total weight of 2, and that's not smart, because if you look ahead, if you look over the entire graph, this situation, it's trivial because it's so small, you can see that you'll do a lot better if you pick all 4 vertices of weight 1, because none of those is connected to any others, and you'll get a total weight of 4. Okay. So the greedy algorithm in this case is a mistake. I'm going to conclude this discussion of undirected networks with another kind of related but quite different, well-known problem that does involve undirected networks. So suppose N is a connected undirected network with the property that its edges actually have positive weight. And suppose that the vertices of N represent cities, and the weight of each edge is the cost of traveling between the corresponding cities. Could be air travel, train travel, bus travel, car travel, UPS, FedEx, all kinds of things, U.S. Post Office. Instead of, in that case, it wouldn't be cities, it would be neighborhoods or houses or something. But this is a problem of very widespread importance. Now, a traveling salesman wants to start at one of the cities and make a round trip covering each city exactly once. And the traveling salesman problem is the problem of finding a way to take this trip that has the smallest cost. So you can see the similarity between the minimum spanning tree problem. But in graph theoretical terms, the traveling salesman's problem is the problem of finding a Hamiltonian cycle rather than a spanning tree in the network that has smallest weight among all Hamiltonian cycles. Well, you can probably guess by now we're headed for trouble because Hamiltonian, whether a graph is Hamiltonian or not is a far more complicated problem than whether a graph has a spanning tree. And in fact, as far as we have been able to determine so far, there is no practical solution. We have never found a practical solution for the traveling salesman problem. I guess the best we can do, I haven't kept up on this very much, but is, computer generated problem, searching through the network with the computer and looking for something small. I'm sure there are, sophisticated tweaks on that. But the greedy algorithm in this case is what is called the nearest neighbor algorithm. So you start at one city and you choose at each step a road of minimum cost. Apparently, as I have read, that leads to a result that is on the average about 25% more costly than the least expensive round trip, which I guess, for small networks, you could use a computer to figure out what the least expensive trip is. And the greedy algorithm, the nearest neighbor algorithm, is not working out very well. And in fact, there are even some circumstances, apparently, that the nearest neighbor algorithm leads to actually the most expensive trip possible. So greedy algorithm is of very limited, if any, use for the traveling salesman problem. Okay, that concludes what I wanted to say about undirected networks. Next, we're going to begin a discussion of directed graphs, which are graphs in which each edge has a direction, and that will lead us subsequently to a discussion of directed networks. So thank you for watching, and I hope to see you in the next video.